Hey guys. Well, today we're going to start talking about acids and bases. And to begin with, just a little bit about acids. Now, acids are something that you have definitely eaten, drank, used on your skin, many different types of acids in the world. And but as far as just a general description, acids taste sour. They produce hydrogen ions, which are called hydronium ions when they're on water, and they have to be on water. So H3O plus is called hydronium ion, H plus hydrogen ion. They're the same thing as far as we're concerned because the hydrogen ion only exists in water. So acids will be in water producing these hydrogen or hydronium ions, H3O plus. And because they're producing ions, acids are good conductors of electricity. Also, acids will react with metals to produce hydrogen gas. And we can always remember that hydrogen gas is a H2 molecule, not just H. So when you're writing reactions to produce hydrogen gas, make sure it's H2. Again, lots of examples of acids in our homes, and citric acid and all kinds of citrus fruits. Vinegar contains acetic acid. In your stomach, you have hydrochloric acid. In your car battery, you have sulfuric acid, H2SO4, and so on. So there's just so many different acids around the house. Bases, on the other hand, bases have a bitter taste. So if you taste an acid, it's sour, but if you taste a base, it's bitter. And soap, all kinds of different soaps contain bases. And so we know that bases also feel slippery. If you've ever gotten soap put in your mouth for any reason, you know that it tastes bitter. Bases produce hydroxide ions, OH minus. So acids produce H plus, bases produce OH minus in water. So a typical base is sodium hydroxide, NaOH. This is like really concentrated. It's like Drano or lye soap has sodium hydroxide in it. And so there's a lot of cleaners that contain different bases. It might be a phosphate. There's bases, there's a lot of weak bases that are like phosphates, carbonates are bases. But the strong bases are the alkali metals with OH or the alkaline earth metals with OH. Those are your strong bases. So potassium hydroxide, lithium hydroxide, the other sodium hydroxide, the other alkaline metals with hydroxide, and the larger alkaline earth metals are strong bases because they dissolve in water. So magnesium hydroxide isn't exactly considered a strong base because it's not soluble, but if you react it with acid, it will completely react and completely give up its OH minus. Okay, so our alkali metals with hydroxide are strong bases, and then the bigger alkaline earth metals with OH are strong bases. So in water, they split up into ions. So bases also conduct electricity because they're producing ions. So one of the oldest definitions of an acid and a base was given by Arrhenius. And Arrhenius said that acids produce H plus ions in solution, and bases have OH minus ions in their formulas, and these will also dissociate or come off in solution. So he was only looking at the H plus on acids and bases that have OH minus ions in their formula. So that describes a lot of acids and bases, but not all. So his is the oldest and simplest definition of acids and bases. And this was way back in the 1800s when he came up with this definition of acids and bases. So again, acids will give a hydrogen to water or to a base. Hydrogens are given off from the acid to water or a base. And in water, it produces H3O plus. If we are not putting the water in there, then we can just split a strong acid up into its ions completely. There's 6 strong acids: HCl, hydrochloric acid, H2SO4, sulfuric acid, HNO3 is called nitric acid, HBr, hydrobromic acid, HI, hydroiodic acid, and HClO4, which is perchloric acid. We will talk about naming acids on a different day, but you should make sure that you write down these 6 strong acids. You need to know the 6 strong acids, and they completely break up into ions in water. Okay, and they all have an H in them that they're donating to water or to a base when they're mixed with a base. We can describe the strength of an acid with what's called a pH scale. And pH is, the formula for it is minus the log of the H3O plus or H plus concentration. Someone decided years ago to make this a logarithmic scale because the hydrogen ion concentration is very small. It'll be like times 10 to the minus something. And but for ease of describing acids and bases, if the pH is a log scale, then we can have it be from between 0 and 14. So anything less than 7 is going to be an acid. So pH of 0, 1, 2, 3, 4, 5, 6.9, those are all acidic. But when it's pH 7, that's perfectly neutral. And then anything above pH 7 up to 14, that's as high as it usually goes, is a base. Okay, so less than 7, acid. Neutral is exactly 7. Higher than 7 is a base. Well, a little bit later, after Arrhenius's definition had not applied to all acids and bases, a second definition was given, which is called the Bronsted-Lowry definition. And the Bronsted-Lowry definition says that an acid is any molecular ion that donates a proton. H plus is just a proton because hydrogen is the element that doesn't have a neutron. So a hydrogen atom is 1 proton and 1 electron. But when it doesn't have the electron, it's just H plus. So that is just a proton. But you can also just say it donates a hydrogen ion to another substance. And then his definition of a base is completely different from the Arrhenius definition. Bronsted-Lowry's base definition says that a base is receiving a proton, or it's a proton acceptor. Okay, so a base is a proton acceptor, and a acid is a proton donor. So proton acceptor, proton donor. So a little bit different definition than Arrhenius. And one of the bases that would fall under this definition is ammonia. Ammonia is the most common weak base that you'll see in the reactions that we look at. And it's NH3. It does not have an OH in it. In water, it will produce OH minus. That's what makes it a base, because it will accept a hydrogen from water and leave the OH minus ion. So in water, NH3 becomes NH4 plus as it picks up an H plus, and what it leaves then is OH minus. So producing OH minus ions makes it a base. Okay, so it does not follow the definition of bases by Arrhenius because it doesn't have an OH in it, but it does produce OH minus ions in water. So it is a proton acceptor. Think of water as HOH when it's reacting. So the ammonia is grabbing that H from water and becoming NH4 plus and then OH minus. So conjugate means partner. The word conjugate means partner. So this base, NH3, when it picks up NH plus, what it becomes is called its conjugate. And it is now an acid. Because if it goes back the other way, then this NH4 will give up or donate the H plus to become NH3. So this is the base, and this is its conjugate acid. If we look at the next example, HCO3 minus is the conjugate base of H2CO3. So H2CO3 is an acid, and when it donates an H plus, what's left over is its conjugate base. Okay, so conjugate just means partner, and if it's a base picking up an H, what it becomes is a conjugate acid. If it's an acid donating an H, what it becomes is its conjugate base. And these are reversible. So if we went back this way, this base could pick up this H plus to form an acid, or this acid could give up an H plus to become a base. Okay, so they are reversible. You can get the conjugate base from the acid or the conjugate acid from the base. So what would be the conjugate base of H2SO4? Well, if it's an acid, to become a base, it has to give up an H plus. So what's the conjugate base of H2SO4? HSO4 minus. So this is losing an H plus. To make its conjugate base. What's the conjugate acid of SO4 minus 2? Well, that means if it's going to become an acid, it has to gain an H plus. Well, when this gains an H plus, it is HSO4 minus. So this one's gaining an H plus. So not only do we add an H into the formula, it changes the charge. In this case, it's losing a plus charge, so it ends up with a -1 charge. In this case, it's gaining a +1 charge, so the -2 becomes a -1. So you will have a reaction shown where you have to be able to identify what's the acid and what's the base on the reactant side. And for our purposes here, we're going to always consider the reactant side being the left side of the equation. And then on the other side, we're going to identify what the conjugate acid is and what the conjugate base is. Okay, so when we're first looking at the reactants, we have to look at what they become, what happens to them. So the H2CO3, as we look over here, it's becoming HCO3 minus. So it had to have lost a hydrogen to do that. That means it's an acid. Acids give up or lose H pluses. What it becomes is its conjugate base. And then if this is the acid, that means that water is acting as a base in this reaction, and bases are proton or hydrogen ion acceptors. So that's what happens to this. It's becoming this. It is gaining an H plus. So it's a base But then when it has the H plus, it's now an acid. So this H2CO3 became HCO3 minus. So the acid became the conjugate base, and now the base gained an H and became its conjugate acid. They could go back the other way. This conjugate acid giving up an H would form H2O. So it going this way, it's acting as an acid. And the same thing here, this conjugate base, to become this, it has to gain an H. So the conjugate base gains an H to become the acid. Okay, so it's a reversible process. The acid becomes its conjugate base when it gives up an H. The base becomes a conjugate acid when it gains an H. And then going back this way, this would be the acid and this would be the base. So let's do another one of those. So I'm going to give you a moment to look at it. Label the acid and base, and we're going to label those on the reactant side. So one of these is the acid, one of these is the base. And then on the product side, one of these is the conjugate acid and the conjugate base. Right? So as I look at these two, it's crucial to look at what they become. So the CN minus is becoming HCN. So what happens to it for it to become HCN? It's grabbing an H, it's accepting an H. So that means it's a base. Versus this one, what's it becoming? It's becoming this. So it's losing an H. So it's the acid. Acids are proton donors or hydrogen donors. Bases are hydrogen or proton acceptors. So this one's gaining one, this one's losing one. And then what they become is exactly the opposite of what they were before. So this is now an acid, and again, conjugate just means partner. So this base became a conjugate acid when it picked up an H. This acid became a conjugate base when it gave up an H. All right, so make sure you know the definitions for Arrhenius acid and base and Bronsted-Lowry acid and base. And you should memorize the 6 strong acids and then know what strong bases are and know that NH3 ammonia is the most common weak base. And we're going to stop right there for today. Tomorrow we will go more into pH and calculating pH and looking more at some different acids and bases.